It's 3 o'clock here in Belgium, so let's get started. I'd like to wish everyone a good morning, good afternoon, or good evening, depending on where in the world you are. It's a very global audience today, so thank you for taking the time out of your day to join our webinar with Port of Antwerp, Detecting Anomalous Vessel Movements with Artificial Intelligence at Port of Antwerp. First, I'd like to introduce you to our two speakers. On the left, we have Bart Adams. Bart is the founder and CTO of xyzt.ai and has held senior leadership positions at Luciad and Hexagon, where he was the product management director and chief innovation officer. Bart holds a PhD in computer science from the KU Leuven and a postdoc from Stanford University. On the right, we have Peter van Baal. Peter is the lead data scientist in the data and analytics team at the Port of Antwerp. He has a master's in economics and data science and has worked as a data science consultant for different companies in a wide range of industries. Peter and his team are working on different AI applications such as computer vision, NLP, speech-to-text, recommender systems, and process mining for different departments at Port of Antwerp to extract value and insights from the data. Thanks for being with us today, Peter. It's much appreciated. So then let's take a look at what Bart and Peter will be presenting to you today. First of all, we'll introduce you to the Port of Antwerp and the business cases for analysing vessel movements. We'll then talk about AI-driven anomaly detection and how all of this work is moving towards a smart digital twin. We'll then wrap up with some key takeaways and lessons learnt. And for some interactivity during the presentation, we'll run two polls as we'd like to know your thoughts on a couple of topics. At the end, we'll then have some time for questions and answers. Before we get started, a few housekeeping rules. If you do have any questions during the webinar, please ask them via the Q&A box or in the chat area. We'll try to answer as many of them as we can, time permitting. Depending on how many we have, if you don't get round to them all, we'll provide answers to your questions directly via email. And yes, the webinar is recorded, and we'll share it after the webinar, and we'll try and do this as soon as possible. So now, without further ado, I'll hand over to Bart and Peter.
Thank you, Joe. Welcome, everyone. Thank you, everyone, for joining our webinar. I'm really pleased to have Peter from Port of Antwerp joining us today. And as you can see on this beautiful video, Port of Antwerp is a very busy port. In fact, it's one of the largest, it's the second largest seaport in Europe. About a year ago, we at xyzt.ai, we started a project together with Port of Antwerp to look into whether we could find anomalous vessel movements happening at the port. And that's what we will present today, the results of, and also the approach taken. So as Joe introduced the agenda, first we're going to talk a little bit about Port of Antwerp to give some context. And then Peter and I will go into the business cases for keeping historic vessel movement data and analyzing this data. And then we will get to the core of our presentation, which is the AI-driven anomaly detection. At the end of the presentation, Peter will also present how this entire work, this entire research fits into the digitalization process or the digitalization strategy of Port of Antwerp. Of course, we'll give some takeaways, lessons learned from the project, and we'll be happy to answer your questions. Peter, the floor is yours.
Thank you, Bart, and thank you for having me on this webinar. I think on a topic that is really interesting. We haven't seen that much effort or similar use cases in the field, so I think it's pretty innovative. And I hope that with this webinar, we can at least inspire some people to do something similar, to think a bit further what they can do with position data of ships. That's what we will talk about. But first, a word on Port of Antwerp. Port of Antwerp is a global port. Like Bart mentioned, we are the second biggest port in Europe and 14th worldwide. As you can see in the slide, we cover a pretty big area. For the soccer fans among us, it's about the equivalent of 17,000 soccer fields, so it's pretty big. And Port of Antwerp is a port that is growing year after year since the last decades, especially in container traffic. And we see that more ships and bigger ships are coming to our port year after year. But our geographical space is also a bit limited. We cannot expand anymore, or not much. So we have to do things in an efficient and a smart way. And therefore, Port of Antwerp is not only trying to be a global port, but also a global smart port. And we invest a lot in digitization, and that's what the 3 topics on the bottom are all about. We are building in our port a digital nervous system. It's a bit inspired by the 5 human senses. We have sensors everywhere in our port, and we try to measure in real time what is happening in our port. Our network of 800 cameras and some operational drones is an example of the digital eyes of our port. We not only measure what is happening, we also bring this information to the users, to the operations, and therefore we are building a digital twin, which is in a certain way a virtual replica of our port that can give people 24/7 a real-time view of what is happening in the port. And the last step, of course, is not to only to measure what is happening, to visualize it, but also to bring some intelligence to it. And then we talk about the artificial intelligence, and that is what this webinar is all about. But let's start with the nervous system maybe. Of course, one important source in the nervous system is the tracking of ships in our ports. And at Port of Antwerp, we use a combination of technologies. So first of all, we have radar towers in the port. Radar towers that are sending out waves, and the reflection of the wave is telling us that something is there on the water, for example. If you would visualize it on a map, you would just see a blob, that something is there, but it does not give much additional information above that. But we also have an IS trackers or receivers in the port. IS is standing for Automatic Identification System, and it finds its origin in the avoidance of vessel collision and vessel tracking. And it's like a GPS signal that's sent out where we can track where a ship is, but it also sends out additional information like the ship name or the ship measurements, the heading and the speed of the ship. And at Port of Antwerp, we combine this radar and this IS information into one single source of truth where a ship is positioned in our ports. Now, why are we tracking vessels? Of course, it's the most important reason is we need in real time a good vision of what is happening in our ports for vessel traffic management. So people involved in planning and in traffic control, they need to get a good view of what is happening in our port in real time. But collecting this data in real time, days or weeks or months or years, it also means that you are building a big history of what is happening in your ports. And until recently, we did not do a lot with that, but it was really a huge amount of data that we had on positions of ships and voyages of ships in our ports. And so we had a contact with xyzt, and we had some brainstorm sessions where we were thinking, isn't it interesting to explore a bit this historic data and to look for patterns in the data that we can learn from, that we can now use in the operations in our digital twin in Port of Antwerp. So maybe some of the use cases, Bart, to go through.
Thank you, Peter. Yeah, so before going deep into the anomaly detection, I wanted together with Peter highlight a couple of business cases where it makes sense to really log the movements of vessels and then do analysis on those historic data sets. And the first one is compliance. If you think about the port is a very complex environment, a very busy environment, a lot of movements, a lot of activities, and of course, all those activities have to follow certain regulations. And when some vessels, for example, don't follow regulations, that can mean there's an issue. The issue can be in efficiency, it can be monetary, but it can also be related to safety. So just looking at the historic data from a compliance point of view can give you insights on where certain processes are going wrong. The second, Peter, is safety.
Yes, of course, safety is of utmost importance for Port of Antwerp. What you see here on the slide on the left is an article of an accident that happened in our port. It was a collision of a ship with our infrastructure with huge damage as a result. On the right, it was not in our port, but it's also collisions between ships that sometimes happen within ports. So a collision is something that you want to avoid at all time, of course. And learning from the history of those accidents, or even the not accidents themselves, but near misses, for example, to see where there are dangerous situations in your ports, and to see if there are patterns in it, and you can learn from the patterns, and you can see, is it possible that similar situations will happen again in the near future. It can show you opportunities to increase your safety in your ports, in fairways and in terminals.
All right, thank you, Peter. And the third one is port performance, very hot topic. These days, also with the whole challenges around the container traffic, for example. And the picture that you see here is actually a picture from our platform. In this case, it's not with data from Port of Antwerp, but it's data from one of our partners, Spire Maritime. And what you see here is basically history of vessel traffic, and those white dots that you see on the map. Those basically are ships at anchor, vessels at anchor, waiting maybe to get into the port to basically get rid of their goods and so on. And measuring the wait times in anchorage areas, or analyzing what is happening in the terminals in the port, can give you insights into the performance of a port. And it allows you to measure, against your competition, and it allows you to improve over time. And then the final one, Peter, is a sustainability topic.
Yes, of course. Last but not least, the environmental aspects. We see that a lot of ports and the shipping industry in general is taking a lot of measures in this energy transition, and Port of Antwerp has the ambition to be climate neutral by 2050. And here also historical data can play an important role to understand from those voyages in your port, to learn if your infrastructure is ready for those new type of green ships, for example, and to see where you need to invest to improve your infrastructure, but also to learn from historic data if there are some less environmental friendly activities happening. For example, the degassing of tankers, which is luckily only rarely happening in the ports. It's more like an anomaly, and here AI can play an important role. And of course, this is what this webinar is all about.
All right, thank you, Peter. So Joe, I think this brings us to our first poll question for the audience.
Yes, we do. So poll question number 1, in your organization, what would be your top priority? The answers are compliance, safety, performance, or sustainability. So let me bring that up for you now. I'll launch the poll. So please go ahead and make your selections or selection. Okay, we'll give it a few more seconds while the last ones are coming in. Okay. Last 1 or 2. I think that's it for now. Okay, great. Let me end the poll and I will share the answers with you. Here we go.
All right, it's interesting. So performance is leading. That's good to know. Fortunately, sustainability is the last one here. No, thank you for your response. And we talked a lot about this historic data. So just let's have a look at what this historic data looks like. And I want to do that by showing a little bit of our platform, xyzt.ai. It's a SaaS platform. It's a cloud platform that allows you to create multiple projects and then ingest lots and lots of historic data. So I'm opening a project here with data from Port of Antwerp. It's actually tanker data, and first I'll show you a little bit around the port using this aerial imagery. So you see there's like multiple docks. You also see here the very special location of the Port of Antwerp, which is quite inland for a seaport, which means that the vessels have to travel quite a bit to get into the port. Now here you see this historic data. So this is the AIS and radar data, and actually it's fused already. And you see here in our platform, you can see that you can plot heat maps of where activity is going on. At the bottom of the screen, you see a timeline, which allows you to filter in time. And basically, this allows you to really explore the data and really quickly answer those questions that you would need to answer look into sustainability in port performance, and so on. So let me show you a couple cases here. So I'm dimming the background layer a bit to let the movement data stand out. And what you see now is a split view analysis. So basically we have the same area in both views, but we filter on different time periods, comparing the left to the right. And that allows you to really see the difference in performance or in the statistics in the data. And if you then apply filters, for example, to only look at certain types of vessels or certain types of activity in the data, you can get insights into how the port is evolving, how the port is changing. Here I show also how you can look at, for example, two different docks, two different areas, and compare the difference in traffic, maybe see which one is more congested than another one, and so on and so forth. This capability we call visual analytics. It's a visual way to analyze what is going on. It also includes capabilities to filter not just in time, not just in space, but also based on attributes, and also to style your data in certain ways. So for example, here I'm styling the data based on the velocity, the speed over ground of the vessels. Where it's blue, it's low velocity. When it's red, it's high velocity. And allowing you to style and filter in those ways allows you to gain insight and explore the data and even spot anomalies in the data. We also do provide dedicated statistical pages which give you more summary statistics on the data. For example, this one gives you trend analytics comparing the last week with the week before. For example, here focusing on a number of areas in the port, couple of the major docks, and there you can see, okay, compared to the week before last week, what is the change in traffic? And the way that is done is basically you can upload your areas of interest, or you can just draw them on the map, like I did here in the demo, to define those areas, and then they become available to do the analysis, for example, in the trend analysis. The platform has many more capabilities, like looking at the distribution of the vessels, or the type of vessels, the distribution of activity, how that changes over time. How does the traffic go from one area to another? That is called origin destination. And you can create dashboards, custom dashboards with this, and then share it with anyone involved in the project. And we actually use this platform a lot during the whole project with Port of Antwerp, especially also to communicate the findings with operational people. That was an easy way for us to, and especially in these COVID times, to be able to share our results and share our insights. So that basically concludes the first part of this webinar, which was talking about Port of Antwerp and the business cases. I would like to dive into the actual research and the actual anomaly detection that we did. I will apologize for maybe some of the more operational people of the technicality, but I'm not going to dive deep into the AI. But Peter and I, we will be happy to answer any questions there. So the goals that we had when we started the project, and we did a lot of brainstorming and we did a lot of interviews with operational people. And in the end, we came with 3 goals that we thought were critical to the project. And the first one is it should be data-driven. If you look at the amount of activities, and you can already see it from the heat maps and so on, there's so much movement in the port day and night at so many different locations. We want to make it data-driven or digital. So as little as possible human intervention. So this also means that we don't want humans to be looking at data, to tag the data, to identify maybe suspicious movement or anomalous movements, and to give that as an input. So everything should be automatic. And by automatic, we mean not just the learning of what is anomalous, but also in allowing the operator to automatically see those anomalies, to automatically help them find the needle in the haystack, so to speak. And finally, one of the third requirements that we figured out by talking to the operational people was that it's all good and well if we can detect the anomalies, but if we cannot explain why it's an anomaly, it becomes less useful. So that's the third requirement, explainability. And that's typically a challenging requirement for AI algorithms. So before going into the algorithm, let me show you one of those anomalies, or maybe two I prepared, that the algorithm detects. So this is a journey of a tanker moving from point A to point B in the port. So you see point A and point B on the map. They're quite close to each other. But what the algorithm found was that this is an anomaly because the tanker moves in a much longer journey than is typical when a vessel moves from point A to point B. Later on, I'll talk a little bit more about this use case and why it's an anomaly, but maybe why it's not suspicious or maybe not even illegal. And it can be perfectly explainable as well. Here's another example. You see the marks A and B on the map, and you immediately see that point A is not where the vessel started. You see it's actually in a different dock. So what happens here is that the captain of the vessel communicated that they would move from point A to point B, but actually they moved from a different location. That by itself is already an anomaly, and that can happen, of course, as well. But on the other hand, we also see, and it's actually I reversed point A and point B on this map, I see. So the start was correct and the end is wrong. No, both are wrong. Sorry, I apologize for that. So it ended up in B, but it continued to a different position, more north of point B. In addition to that, the movement was happening at night, which by itself is not an anomaly, and it's perfectly normal to have movements at night. But in addition, also, there were many stops in between, and that becomes more anomaly again. So you see, it's a combination of these different aspects that can lead for the algorithm to define a journey or a trajectory within the port as an anomaly. So before going into the algorithms that we investigated and tried out, let me first talk about the data sources used. We already talked a lot about AIS and radar data, but one of the also important data sources is called APIX, which is a system at Port of Antwerp that is basically a database or keeping a database of all the activities happening in the port. So enter, exit, registrations, origins, destinations, and so on for all the different vessels. And that system is really valuable because things that are not in the system are probably already an anomaly by themselves. So we talked about AIS. For those of you not familiar with AIS, it's basically the vessel itself that is communicating its GPS location, but also in addition communicating a lot of properties like what is the ship type, what is the status of the ship, what is the identifier of the ship. And of course, this signal can be turned off or it can be tampered with. Like you could communicate a different activity than the one that you're actually doing. For example, for fishing vessels at sea, sometimes they report that they're not fishing, even though they're fishing. But in a port, that can also happen. The other data source, as Peter said, is radar. It basically gives you a blip at a certain position at a certain timestamp. And those two data sources, they're fused together. So AIS and radar are fused together to have one source of truth, so to speak. And then finally, we also used geospatial data sources, so GIS data sources. And I'll explain a little bit later on why those data sources are so important. So the GIS data sources also give us information on where are the locks, where are the terminals, where are certain locations from the history or from the past where there were suspicious transactions and so on. So all these data sources, they're basically fused together in the first step in the algorithm. And the output of this first step, very simplified, is a series of trajectories or journeys, or you can call it movement paths. And it's not just the geometry, it's not just the locations with timestamps associated to them, but it's also, we also tagged along the trajectory important events. Like, for example, the trajectory starts at a certain terminal, or the vessel stops at a certain location. So all those dots, they're computed during this data fusion process, and they're completely automatic. And let me show you with the trajectory in a short movie what is actually happening in the algorithm. So, and don't worry, this is going to repeat one more time for you to follow. So you see this blue trajectory, it's actually a vessel moving from the left side all the way to the right side. So you see it starting, it stops in a lock, it stops in another lock, it makes a turn, then it stops again, it does another stop, and then finally it moves to its final destination all the way to the east of the port. So what the algorithm does is basically the following. So it has the whole geometry of the trajectory. It gets that from the AIS data fused with the radar data. And then it uses all the other data sources to tag the trajectory along its route. And it starts at the beginning. So first, it looks into the database whether the start location is actually indeed what is reported in the database. So if in the database it says the journey starts at Frasenedok, it does a geospatial query, a geospatial analysis. Is that the location where it's actually starting off? It also detects stops. So the algorithm detects stops, but in this case, it identifies that the stop is in a lock, which is perfectly normal because there the vessel has to wait to continue its journey. Here's another stop. Here's another stop, which is not inside the lock, another stop. And then finally, there's an end stop, which is actually, according to the database, should be in the Leopold dock. And for those of you who know Port of Antwerp, that final location is not Leopold dock. So it's a different location. And we tag the trajectory with the fact that this is a wrong location. And all this becomes the input of the algorithm. And that algorithm we call the ranking algorithm. So basically on the left side, you see a big bag of hundreds of thousands of trajectories or journeys of different vessels over the past months or years. Those go into an algorithm, a ranking algorithm, and out comes a list of trajectories basically sorted from least suspicious or least anomalous to most anomalous. And that's what we try to color code here. So the trajectory at the bottom, the green one, is maybe a very normal one, a very common one. The one at the top, color coded in red, is a very special one. So how do you detect these anomalies? And this is where it becomes a little bit technical. In fact, we investigated two approaches. The first one is using neural networks, using autoencoders. And very simply said, what happens in such a network is that you take a trajectory or those feature vectors, and basically you try to reduce the dimensionality. You try to project it to a lower dimensional space and then reproject it to the higher dimensional space. And you train a network like that by ingesting it with lots of data and getting outputs for all these trajectories. And basically what the trajectory is optimizing for is it's trying to make the weights of the whole network so that the trajectory that gets out of the network, the output of this algorithm, is as close as possible a match to the input. So basically it tries to reduce the dimensionality, increase the dimensionality by reconstructing the trajectory again. And you can think of this as the same what you can do with image compression. You have a very high resolution image, you compress it to a very pixelated, low resolution, but small in size. And then you try from that low resolution representation to get back to the original image. And the algorithm tries to minimize the error made in that process. And this is a way to learn a network that can detect anomalies. Because basically what the network does, it tries to learn what is normal, what is common. And if you then get a trajectory that is not normal, you will get something like what is shown in this picture. So the input trajectory maybe looks like this, and the output trajectory looks like this. And you can see it's quite different. And so the difference basically between the input and the output is a measure for oddness or for anomaly, anomaly detection. It's very easy to implement for those of you who are familiar with Python and all the toolkits. It's maybe 10 lines of code in the end. Of course, this excludes the whole data fusion process. It's fast to evaluate once trained. The training, on the other hand, can be quite complex, can be computationally intensive. It's also quite difficult to tweak in my experience. And one of the reasons is also that you have to avoid implementing a one-to-one copy, meaning that you just copy the input to the output. And the biggest drawback for us was that it doesn't give an explanation. It's a black box. What something comes out, and yeah, you see that indeed it's abnormal. It's different from the others, but you don't really know why. The second approach that we followed is called k-nearest neighbors. It's a very old machine learning approach where you take lots and lots of input data and you try to figure out what is different in the data, basically using the following process. So say you have a trajectory like this, say a movement from one vessel from one area to another area. What the algorithm does is it basically looks for the nearest other trajectory. And let's assume it's this one, it's this gray one. And it does so in a repeated fashion. So it doesn't just look for the first nearest, but also for the second nearest, the third nearest, and so on, until you reach this number k. And k typically you take anything from 1 to 20, 30, whatever you find. And then when you compute the distance between a trajectory and its nearest trajectory, you sort of get a measure of oddness. It's different from the others. But if you would just look at one nearest, maybe that one nearest is the odd one, is a special one. So that's why you look at multiple nearest ones. And in this case, you can see all the gray ones, they follow the same journey. The blue one follows a different journey. What are the pros of this approach? I think the biggest advantage of using this approach is that you get an explanation right away. Basically, by looking at the nearest trajectories, you immediately see what is different from the trajectory that you're analyzing. And that explains why that trajectory is an anomaly. It's also quite easy to tweak. You can tweak with the weights. You can try different distance measures and so on. The main difficulty is how do you define what's the distance between two trajectories? And now we get into geometry and topology. But basically, there's a really nice approach which is used a lot in time series analysis, where you have like a one-dimensional function. And it works by basically doing time warping. So basically, you take two trajectories, and instead of just computing like a Euclidean distance between those two trajectories, you warp the trajectories in this process so that in time, so that they align better. And that gives you a better measure of how they are different. And you can include all those different metrics that we talked about. I wanted to show you this little image to further highlight the complexity sort of the problem. It's a real topological problem. So for example, what you see here, at the top of the screen, you see the bevrijdingsdok, which is a big dock at Port of Antwerp, and then you see deurgangdok at the bottom. And then I highlighted in this gray-white color all the movements from the bevrijdingsdok to the deurgangdok for a couple of days. And you see that there's actually two common routes. There's this first blue one going to the left, and then there's this second green one going to the right. So in your algorithm, you have to be careful not to say that the route following the second route is an anomaly because it's so different from the first route. And in fact, it's quite different. The distance is different. The geographical location is different. Probably the speed and the velocity is different and so on. So that's why you need a lot of data, and you need to be careful not to really just use the first nearest or just a few nearest neighbors. So you need to be quite robust against these cases. And this is even a simple case in the port. There's so many different ways that vessels can move from one area to another. The reason they do that is, of course, because sometimes a certain lock is busy and they prefer to go around, which is perfectly normal, of course, in a port. So just to summarize this part, and I'm going to show you a few more results. We chose in the end to use k nearest neighbor. We use 10 nearest neighbors. We don't use a uniform weight. We use an average weight that is weighted by the distance. So the first nearest neighbor has a bigger weight than the second, and so on and so forth. In the end, this distance measure gives you a number, and that number we normalize between 0 and 1,000. And then if the number is 0, it's a very common journey. It means that for that journey, the nearest, the second, the third, and the 10th nearest neighbors have a 0 distance with that journey. So they're all the same. So it's happening 10 times at least over the course of the period we're analyzing. On the right in the little box, you see all the different features or all the different properties that we took into the algorithm. So of course, we took the trajectory itself, the geometry, but we also took the travel distance, the travel time, the number of stops, whether it's a seagoing vessel or not, which is quite important. Of course, the type of the vessel, I didn't even put it on here. Whether the travel is at night or not, whether the stops are at special locations. So we knew from the port police, for example, that there are special locations where sometimes activities happen. Whether the journey was reported or not, whether it was reported or correctly or not. So all these properties we took into account into the algorithm to do the ranking. For those of you affiliated with Port of Antwerp, or maybe those of you not affiliated with Port of Antwerp, don't worry. There are very few anomalies, and you can see that from the distribution. The distribution is a very long-tailed one. So actually what you see is this ranking, this number that I explained, that when it's 0, there's no anomaly. When it's 1,000, it's really a special journey. You can see that 99% is below this number 230, and you also see it from the distribution that there's very few very high numbers. So let me show you a few of the results in a replay in our platform. And let's first look at I think one cargo vessel. So this is basically we split up in the project. We split up cargo traffic from container traffic, from the tanker traffic. Here you see the heat map of all the location records that we used. So you see it's from beginning of June to the end of November, so half a year of data. Here I put on a dashboard a couple examples. This one, the end is wrong. It's happening at night, and the topology or the geometry of the movement is very different from what is happening. So you see it's starting there on the east side of the port. It's going north, and then it's going south. It does a number of stops in between, goes back and forth between different areas. So it's a very different trajectory than what you would see from other trajectories, saying that they go from I think that's also the Vrijdingsdok to the Deurgangdok. So that came out as an anomaly. Here I'm switching to the cargo, to the tanker vessels, and that brings me back to what Peter talked about before. Is this possibility of illegal degassing. And illegal degassing happens with tankers when basically they have to change contents from one type of fluid to another type of fluid. And they have to basically clean the tanks and empty the tanks. And that sometimes happens by during moving around and then letting the remaining gases get out of the tank. So what you see here, this red trajectory, and I'm trying to move really slow here, you see that it's moving to the north of Antwerp, the Port of Antwerp, and then coming back. So I think I'm going to repeat it now again so that you can see it again. So you see it's starting there, it's going north, and it's coming back. It's just immediately. And that's really suspicious, or it's different from normal behavior. It's not something that we see a lot in the data. And that could be an indication of an illegal or a possible degassing event. Here also is an example. And here it actually happens 2 times. So you see here at the bottom of the screen, the red trajectory is going all the way up to the River Scheldt. That's the big river to the North Sea. It gets back, like here, let me show that again. It goes back into the port area, goes through a lock, and then it goes north towards the Netherlands. It comes back and it stops. So that's also a movement or a trajectory that we don't see a lot in the data, and that the algorithm spotted, basically mostly because of the long journey. So here it's one more time for you to follow how it moves over time. So our platform allows us to not just look at the whole distribution of the data, but also to highlight certain trajectories, certain movements, and then communicate that with the stakeholders. Here's another one, a final one that I wanted to show. And here I wanted to explain a little bit that these types of movements that you see, they are an anomaly. They're not happening a lot in the data, but it's not proof that something is wrong. For example, what could have happened here is that the vessel was going on a task to one of the terminals in the lower right corner of the map, but then maybe there was like something cancelled or there was congestion and it moved back to maybe a second task, another terminal. So that's could perfectly happen. So there's no real indication that something is really wrong here, but it is different from what we see in the majority of the data that the algorithm detected. So that brings me to the lessons learned from this project. The first one is we're dealing with a lot of data. If you think about years of movement data in major international port, it quickly gets into the billions and billions of data points. And of course, you're working on algorithms, you're tweaking algorithms, so you have to make sure that things are automated when you train and validate to avoid losing time on those aspects. So it's not just automation for the operational people, for when you deploy certain algorithms, it's also during building the algorithms. The second thing that we learned is that context is extremely important. So just from the geometry itself, it's really hard to find anomalies or to really find useful anomalies. The location of a stop, the type of a vessel, the time of the day, all those aspects together, they give more context and they help the algorithm to give better results. Another thing that we did early on, and that's really thanks to Peter also, is we involved the stakeholders from Port of Antwerp. So these are people from the vessel tracking department, but also from the sea police, operational people, planners, and so on. And we involved them from the beginning with interviews, with feedback, and also when we showed first results. And every time we got back with more information, more insights, maybe explanations to why something is happening and why something is indeed maybe an anomaly. Another important aspect is when you start looking at movement data is that we can't be really judgmental in a sense that it's not black and white. An anomaly can be just a new observation. Maybe it didn't happen in the last year or the last 2 years of data, and now it's happening, and maybe there's a good reason for it. But it can be a good indication of something to look at. And that also relates to the final lesson learned, is that especially in the case of anomaly detection, I would be very careful with doing a binary ranking or a binary decision, whether to say yes, it's an anomaly, or no, it's not an anomaly. I rather prefer a continuous ranking, which is sometimes called a degree of interest ranking, and present that to operational people so that they can sort of focus their effort on the most anomalous ones, but still make a judgment that involves maybe some expertise they build up over years. So Joe, that concludes my part. And before we go into the bigger story with Port of Antwerp, I have one final poll for the audience.
Yeah, great. Thank you, Bart. So poll question number 2, what is the data maturity in your organization? So the answers are data. Where do I get it? We gather data, but it's sitting in our data lake. We are experimenting with data analytics, or we embed data analytics in our business processes. So let me bring up the poll. There we go. And if you would make your choices, please. give a few more seconds while the last ones come in. Okay, we'll close the poll there and let me just share the results with you.
All right, that's nice to see. So definitely there's this ladder, and most of us are in the final stage. So that's really great to see, and that's also what we experience with a lot of our customers and people partners that we talk to.
Wonderful, thank you. And let me just remind you, if you do have any questions, then please go ahead and put them into the Q&A box or into the chat box. Thanks.
Right. Thank you, Joe. So basically, that concludes the second part, and then I want to hand over to Peter to talk a little bit about the bigger smart digital twin project at Port of Antwerp. Peter?
Yeah, thank you very much, Bart, and thank you for the very clear explanation on this sometimes a bit challenging topic, as we experienced in the past months. So where does all this, where does this use case bring us? If we would go back to the beginning of the presentation, we talked about a digital nervous system and a digital brain. So I think it's pretty clear from what Bart showed that we worked with sensor data or tracking data, and that we added some intelligence to it, the AI part. And now we want to bring this information to our operational colleagues in the digital twin, so the replica of our port, the virtual replica. So this use case, are we going to put it directly into digital twin and give it to port authority and ask them to start penalizing vessels that are having a high anomaly score? Of course, we will not work like that, because like Bart explained, a high anomaly score does not necessarily mean that the ship is doing something wrong. It can just be a kind of behavior that we haven't seen very often in the past. So it's perfect. It can be perfectly normal behavior. But it is an interesting additional information source that we can bring to a digital twin, and which we would like to combine with other data sources. For example, if we have sensors in our port that are measuring the air quality, and we know that the ship in the neighborhood of that sensor is having a high anomaly score and doing something strange, and we know, for example, that the wind is coming from a certain direction, we might, if we link all those data sources together, have an idea that the ship is, for example, doing some degassing in the port. So it's really to get a situational awareness, or to bring situational awareness to our operational people and to help them acting on that. And that's what the next video on APICA, which is the Advanced Port and Information and Control Assistant, is really all about.
Good morning and welcome back. General status report. Today is an overall sunny day, with a light breeze from the northwest. Port traffic is busy as usual at this time of day, with 221 barges and 180 seagoing vessels in port. We're expecting 95 new arrivals and 73 departures today. Road mobility is within efficiency norms. There are 2 INOS quality alerts and 1 ongoing event. Would you like to investigate? At 8:51, INOS 22 detected possible hazardous compounds. Analyzing. According to historic wind data and ship tracking, a possible cause might be the chemical tanker My Fair Lady. Would you like to collect an air sample? Please select available UAV. Calculating flight trajectory. ETA in 1 minute 30 seconds. Initiate. Confirmed. I am APICA. Welcome to the port of the future.
All right. Thank you, Peter. So that brings me to the takeaways for you. thank you again for attending. The first takeaway is that vessel tracking, it really has business cases beyond the real-time use case. So it has business cases to improve efficiency, to improve safety, to basically monitor sustainability and so on, as we talked about. So that's the first takeaway. So if you aren't yet using historic data, or storing even historic data, it might make sense to start logging the data and making sure you have it available to do your analysis. The second one is that technologies exist, and of course, this is where we also come in with xyzt.ai. Technologies exist to visualize this type of data. It's not easy data. It's complex data. It's quite big data. But for sure, we can help you if needed to help you solve your problems there. And then finally, creating some FUD here. From seeing this presentation, you know that Port of Antwerp is on this journey. They're of course very innovative and at the forefront of this digitalization process. But you can be sure that your competitor is doing this also. So whether you're in port business, in shipping business, in logistics, be sure that your competitor is doing these types of things using AI, using advanced technologies to use historic data to get a competitive edge. So don't get left behind. That's my message here. But from the poll, I see that almost 50% of us is on this journey already. So that's good. That's good to know. So I would like to thank Peter once more. I would like to thank you, and feel free to ask any questions.
Great, thank you, Bart. Okay, so let's have a look at what has come in. So the first one is the input of the data based on publicly available data such as marine traffic, or what is the exact data you require from a port authority in order to make these analyses?
Peter, do you want to answer maybe the first part of this question?
Yeah, I think I can answer it, but you can probably go further with it because let me first give my answer. Is that this exercise is based on data of Port of Antwerp from our IS and radar systems, as we explained in the beginning. So it's not public data, but it's data of the port itself. But Bart, I think it's those kind of exercises are not only limited to this type of data.
Yeah, what's maybe a bit special about the data from Port of Antwerp, because it's a fusion of AIS and radar, and the radar is very high frequent in time. So you have a very high resolution sampling of where things are, which makes that you have very detailed movement trajectories. Of course, many of you know what issues you can have with radar, shadowing and reflection and so on. But all of that is fused with AIS. The algorithms could work also just with AIS data. But of course, the temporal resolution might be less, but I don't expect any problems there. But yeah, to summarize, we used data that Port of Antwerp captured and was already logging in their data lake before we started the project.
Great, thank you. One for you, Peter, here. How do you involve your stakeholders, and how do you get the good feedback from them?
Of course, we inspire them in the beginning of the project with the idea, and they pretty quickly were into it. But then I think one of the advantages is the visibility of and the user friendliness of the xyzt platform itself. So if we got some results, it was pretty easy to visualize them in the platform, or even to select some results and share the platform with the users, to give them a login and to explore the results a bit themselves. So I think the main advantage for maybe a more complex thing that we are investigating is that you can easily show the results and share it with your business by using this platform.
Great, thank you. And another one, yeah, what is the business case results?
Yeah, that's maybe one I will answer to as well, Bert. Well, I think I try to explain it maybe a bit at the end of the video, where we really try to create a good situational awareness for our operational people. So it's not that we have one specific business case that we are looking at. We just want to, in all those ships going through our port, the hundreds of ships a day, manual people, a person itself, it cannot start detecting or analyzing ships himself all the time. So we need to support them a bit by some data-driven and AI-driven insights, and that's what this is all about. Is just to support our people and to help them in managing and doing their job, yeah, the best they can, let's say. And it's for a pretty broad audience. We talked about the degassing a little bit, so the environmental people of a department is involved, but also for traffic management, for safety reasons. So people from different departments are involved in the exercise, and also there are benefits a bit for all of them in this use case.
Great, thank you. One for you now, Bart. Well, two parts to this one. Can you use your algorithm to cluster trajectories in groups of similar ones and then compute the statistics on those, or is it only for detecting anomalies? Yeah, what happens if a vessel turns the AIS off?
Okay, that's an interesting one. Yeah, so the clustering is an interesting one. We thought of doing it during the project at some point. We didn't end up doing it. But there are algorithms similar to the k-nearest neighbor, k-means clustering, and so on, that might be interesting to look at. And I definitely think it can be a good way forward to sort of summarize the topology and the movement behavior within a port, so that you get a very concise representation of the typical movements, the typical routes that ships are taking. And then the second question was around
what if they turn off the AIS? Yeah.
What if the AIS is turned off? Yeah, so that can happen. In this case, because the data is a fusion between the radar data and the AIS data. I believe the fusion algorithms, but I'm not an expert on those because it's not our stuff. They do some sort of tracking, basically fusing two sources, and when one source falls away, they are smart in knowing that it's the same vessel still. So most likely we would still see the vessel and still know the vessel from the data. So that's where radar can help a lot. And also what Peter explained is, I believe in the future also the combination with video can help a lot, especially to make an identification on a vessel. That is really easy with image detection, with AI using image recognition and so on, to classify or detect which vessel it is. And then if you then only have radar, you can still make an educated guess of what the vessel is.
Yeah, thank you. And then very simple last one for Peter. Is it possible to get a copy of the APIC video? Is that online anywhere, or can people access it?
Yeah, the Apica video, it's public on YouTube, I think. So if you go to YouTube and you search for Apica, you probably will find the video there as well.
All right, great, thank you. Okay, so we are at the end. It is 1 minute to 4 here in Belgium. So again, I'd really like to thank you, Peter, for joining us. It's really much appreciated for sharing your knowledge and your insight. Thank you again to you, Bart, for doing the presentation. Thank you to everyone that has joined us today. As I mentioned at the beginning, then we will send a recording of the webinar to you. So please view it, share it with your colleagues and things. But if you have any questions, then please reach out. And I would like to wish you all a very good rest of your day and hope to see you again for our next webinar. Thank you very much.